And good evening, AP Physics students. Mr. Kirsten coming at you here. Good to see you. Glad you're here with us tonight. We have a special bonus video today. We're going to tackle not one but two problems from chapter 17. We're going to tackle all of problem 17 and just a little bit of problem 18 to get you going. Well, let's dive right in here. Problem 17 states, to draw a conductor the shape of a football that carries a negative charge Q, draw on 12 electric field lines and 2 equal potential lines. Now, I know what you're thinking, Mr. Kirsten, what is an equipotential line? Well, equipotential lines are lines on which all points along the line have the same potential. So let's draw some in so you can kind of get a feel for what they might look like. Okay, so I'm going to draw a conductor that looks like a football. All right, so maybe about that shape, right? And it has charge minus Q, we're told. Well, we already know what the electric field lines like this would look like. It's negative, so the electric field lines would be pointing towards the football. This being a conductor, we know that the electric field lines would be perpendicular to the surface at the surface, right? Right? So the electric field lines are perpendicular at the surface of the conductor, right? They got to be perpendicular because if there was a component parallel, then the charges on the conductor would move around, and we know that doesn't happen. So this is what the electric field lines would look like around the conductor. Okay, remember the formula that the potential due to a point charge is KQ over R. So I might suspect, like if this was a point charge, if I was the same distance R away from the conducting surface, I would have the same potential. Well, if I have the same potential here, 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 and here, I could draw in a line that represents an equipotential line. And a lot of times, not to confuse equipotential line, with electric field lines, we draw these in dotted line fashion and no arrows. So this is two equipotential lines. So you might think, okay, Q is negative here, right? So maybe this point here has a potential of minus 5 volts, and this point here has a potential of minus, let's see, pardon me, this would be minus 5 volts, this might be minus 2.5 volts, right? Because as R got smaller here, V would get bigger. So that means every point along this line would be minus 2.5 volts. Every point along this line would have a potential of minus 5 volts. I could then say calculate the change in potential energy in moving from this equipotential line to this equipotential line. So for instance, if I moved a 1 coulomb charge from here to here, I would do 2.5 joules worth of work, or I would change the potential energy of the charge by 2.5 joules. Okay? So those are equipotential lines. They're kind of hard to think about, so I came up with a little idea a while ago on a good way to explain equipotential lines. Believe it or not, you've seen equipotential lines before, just not electricity and magnetism like equipotential lines, but gravitational equipotential lines. They're called contour lines in maps. So for instance, I have a map here of the Superior Hiking Trail. So here's a map of Gooseberry Falls. And what are all of these lines in here? These are equal potential gravitational potential lines. In other words, all objects along this point would have the same gravitational potential. In other words, you do no work if you against gravity if you move along one of these lines. You only do work if you move perpendicular to the lines, just like in here. And just like if you had a bunch of lines together here, that represents a really steep slope, right? Because you'd be falling many, many feet over a short distance. Many, many equal potential lines spaced close together would indicate a really large electric field. So I kind of think of contour lines on a map as kind of like equal potential lines. Here we're using gravity, here we're using electricity and magnetism. Okay? Okay, well, let's give you some hints. Oh, by the way, I can't remember if I said. So I think I said electric field lines. Electric field lines are always perpendicular to a conductor at the surface. I can't remember if I said that equal potential lines should always be perpendicular to the electric field lines. That's the way we drew them, but that's the way that always works. Okay, so nice and perpendicular there. Again, if they weren't perpendicular, there'd be a component of the field parallel to the equal potential line, and then you do work as you moved along the equal potential line, which we know doesn't happen. Okay, folks, I'm going to give you some hints on problem number 18 here. For part A, it says find the potential due to a point charge. And I forget the details, but I'm not going to work it all out, but I'm just going to give you a hint that this is the formula that you should use to calculate the potential a certain distance away from a proton. This is our formula for calculating potential due to a point charge. All right. So to get more specific here, I think you use QE over R. Now, if I wanted to calculate change in potential energy using this formula, I would just use this formula, where a change in potential corresponds to a change in potential energy. And I'm going to kind of illustrate this in part B. Part B says, how much potential energy is stored when I have two protons that are a certain distance r apart? Right? How much potential energy is stored there? For instance, if I let go of these protons, they would push away from each other and acquire kinetic energy. So how much potential energy is stored here? Well, one way I can think about it is, let's say I started with one proton really, really far away. So far away it's almost off the screen. It's at infinity. Well, at infinity, or really, really far away as physicists would call it, so they don't get in trouble with their math teachers, the potential is defined to be 0. So I can figure out how much energy, potential energy, is contained in a system by calculating the potential difference between, say, a point very far away, say at infinity, and right here. So call this point A, call this potential point B, all right? And if I figure out what potential this point is at by using this formula here, okay, I can figure out the potential difference between infinity and this point. And once I know the change in potential between those 2 points, I could calculate how much potential energy would be stored in this system. So those are some hints on how to do problem 18, and of course problem 17 worked out in full fashion there. All right, nice work, AP Physics students. I can't remember if I've used this fun picture as your reward or not before, but here it is. This is Mr. Kirsten in 3rd grade. Oh, look at those 2 front teeth. Oh, good picture. Good picture. Isn't that fun? Oh, good stuff. All right, nice work, AP Physics students. We'll see you tomorrow.